So I say I'm never too sure how many of you can you just tell me, shout out if you can see the screen clearly.
I can see the screen.
Yeah. Right. Okay. Yeah. And those of you who can't, that's New Balance. Look at the content. Okay. So I just wanted to find what a diagonal matrix is. That's easily done. We've mentioned it before. A diagonal matrix, I don't think I need to say anything. It says that it's zeros everywhere apart from the leading diagonal going from top left to the bottom right. But I want to interpret what the geometric transformation is represented by a diagonal matrix is. In other words, if we pre-multiply a matrix representing a shape by 2, 0, 0, minus 3, what effect does that have on the shape? Michael, you've got your hand up?
Isn't it stretch in the x direction for the factor of 2 and stretch in y direction in the factor of -3?
Good. So exactly right. So we call that a two-way stretch. Parallel to the x-axis, scale factor 2, parallel to y. And I'm happy to see that scale factor -3, but we might want to say it's a reflection in the x-axis as well. So we might want to describe it as a reflection in a stretch. Okay. 2, 0, 0, 0, minus 3, 0, 0, 0, half is obviously it's a three-dimensional matrix. It's a three-way stretch. So you stretch everything parallel to the x-axis, a factor of 2, to the y-axis -3, and the z-axis factor of half. X-axis -3 parallel to y-axis. So that's a reflection in the xz plane. Stretch. And it's not a squash. Some of you are quite bad at using the right language. It's not a squash factor. It is a stretch scale factor half parallel to the z-axis. So as an example, if we take the matrix 6, 0, 6, 4, 9, 2, 0, 2, -2, and we pre-multiply by this matrix, the one I just talked about, we will get, and you can check. I want to check that I've got it right, in fact. 6. In other words, all the x coordinates have been doubled, all the y coordinates have been multiplied by -3, and all the z coordinates have been multiplied by half. And so 6, 4, 0 has gone to 12 minus 12, 0, for example. Okay. Any questions so far? I don't think it's too hard so far, as long as you can see it. Any questions on that? So we see that if we pre-multiply by a diagonal matrix, it has the effect of doing a three-way stretch, fine. And similarly, it's got the effect of multiplying all the columns, all the rows by the corresponding number in the diagonal matrix. The first row has been doubled, the second row has been multiplied by -2, the third row has been multiplied by half. Okay, now, but what I want to do now is look at what happens if I take a matrix and I post-multiply it by a diagonal matrix. Now, we can't think of that as being applying a transformation to our matrix M. When we're thinking about geometric transformations, we're pre-multiplying. So I don't want you to think of this geometrically, I just want to see what effect post-multiplying that matrix by a diagonal matrix has. Robert, what do you get as your answer for that matrix multiplication there? Oh, Robert, you there?
Yeah, sorry, I've muted myself. I think it should be. Not really sure of that. But
Okay, well, just multiply.
You was like, what was it, 12? So I'm sorry, what was your question again?
Well, the question I want to know is what effect post-multiplying that matrix M by the diagonal matrix has. But if you can't see it straight off, all I want you to be able to do is multiply them. So Robert, what do you get when you multiply those two matrices?
So, what's the question is about? Answer the what's the multiple of the MD?
Yes.
So I think should be similar to the
No, it's not the same as dm. Matrix multiplying is not commutative. So just multiply the matrices and tell me what you get.
So 12 and can I still say that?
Just tell me this, just read out the numbers you get, Robert.
Maybe 12, 0.
12, okay.
0.
Yeah.
0.
Sure. It feels like you're not very confident of matrix multiplication. I don't know how you managed the last exercise.
Right, so can you hear me now?
Yeah, so 12, 0.
12, 0. And then what is it? I think 0.
No, okay. I don't know how you got through the last exercise if you're having trouble multiplying matrices. Okay, Lucy, what do you get if you multiply those two matrices? Can you help out?
Is it 12, 0, 3?
Yeah.
Minus 27. Wait, no, I was looking at the wrong column. Sorry, 8 minus 27, 1.
Yeah, and the last one?
0 minus 6 minus 1.
0 minus 6 minus 1. Good, okay. Now, can anyone see a way of describing what is not after a geometric answer, but what's the relationship? How could we describe what happens to this matrix using words? Yes, Joe.
You've times the first column by 3, you've times the second column by minus 3, and you've divided the third column by 2.
Okay, I think you misspoke, but you've got the right idea. The first column we multiplied by 2, haven't we? The second column we multiplied by minus 3, yeah, that's what it meant. And the third column we multiplied by half. So post-multiplicity has multiplied each column by the corresponding diagonal element. You multiply the first column by 2, the second column by minus 3, and the third column by half. Here, each row was multiplied by the corresponding Now, the thing is that what I've just done is often taken as obvious in the work we're about to do. It's often taken as obvious that you can see what effect post-multiplying and pre-multiplying by a diagonal element has. Some of you were probably there a while ago, but now you need to know that. You need to know that if you pre-multiply by a diagonal element, you multiply the rows. If you post-multiply, you multiply the columns. And that's going to be useful for us. Okay. Any questions on that? Okay, Robin, you might want to practice a bit of matrix multiplication. Okay. All right, okay. Back onto looking at eigen. Yeah, sorry, is there a question? Okay, back to looking at eigenvectors. I've got a matrix, a 2 by 2 matrix. We'll use the same one we've been using, which is n here, 4, 2, 1, 3. That's my 2 by 2 matrix. That's what I'm going to be using. And I'm going to find its eigenvalues and eigenvectors. In fact, we already did that when we introduced eigenvectors and eigenvalues. This is the matrix I used. So way back in the notes, we've already found its eigenvectors are -1, 1 and 2, 1 with the corresponding eigenvalues of 2, 5. Which of course means, and I'm going to pick on someone to check that they understand, remember what it means, which of course means that 4, 2, 1, 3 times -1, 1 must equal what, Casper?
It's going to equal -2, 2.
Yeah. Now, did you do that by multiplying it out, or did you use it do it by using the fact that they were eigenvalues?
No, because minus. I used it using the fact that they're eigen.
Yeah, great. So that's what I wanted. Because that's an eigenvector with eigenvalue 2, it means by definition that 4, 2, 1, 3 times -1, 1 must be 2 lots of -1, 1, which you can confirm by doing the multiplication. And it should work. And likewise, 4, 2, 1, 3 times 2, 1. Well, 2, 1 is an eigenvector, which means if you multiply it by the matrix, you get a multiple of the eigenvector, and that multiple is 5. Okay. Now, we could actually represent that as a single matrix multiplication. If I do the first bit for you, using what I've just taught you, what we were just looking at the start of the lesson, can anyone fill out those two matrices? So I want to write 4, 2, 1, 3, -1, 1, -1, 2, 1, 1. I could write it as another matrix multiplication using some of the theory I just had.
So, can we apply matrix transformations?
It's not about matrix transformations. That is using eigenvalues and eigenvectors and using what I was just teaching you about diagonal, the effect of multiplying by diagonal. I'll tell you, one of those matrices on the right, one of the matrices I want on the right is a diagonal matrix.
So,
yeah.
When we did the matrix multiplication above, aren't they not compatible for multiplication because it's a 2 by 2 and a 1 by 2? Or am I just going to be confused? Because you write them out.
You say you're not happy with this multiplication here?
Because it's a 2 by 2.
Doesn't matter.
No, it's 2 by 2 and 2 by 1. Sorry.
Yeah.
Okay, it's fine.
Yeah. Can you check that you can 4 times -1 plus 2 times 1 is -2. 1 times -1 plus 3 times 1 is 2. Yeah.
Yeah. Okay. Yeah.
So I'm looking for a diagonal matrix to go down here. Kelvin.
Okay. Is it -121112005?
Yeah. Very good. Okay, so have a look at what that does. Remember, we found that if you post multiply by a diagonal matrix, it has the effect of multiplying that column. So if we multiply this matrix by 2, 0, 0, 5, we will be multiplying the first column by 2 and the second column by 5. And if we look at what we're supposed to get, I'll put it in brackets, it does equal 2 lots of, and 5 lots of 2, 1. But not that I'm actually interested in doing that multiplication. I'm not actually interested in what it multiplies. What I'm interested in is showing how I've used the eigenvectors, the matrix of eigenvectors, we can call this, to write matrix times matrix of eigenvectors is matrix of eigenvectors times this diagonal matrix. Okay. Check you've understood all of that reasoning from above.
So why do we put the eigenvector first in front of the eigenvalues?
Okay, I mean, what I could say is what I want to achieve is I want to achieve something equivalent. Here I've said matrix times vector is 2 times the vector. Here I've said matrix times the vector is 5 times the vector. What I want to achieve is something similar. Matrix times the matrix is some multiple of each column. So if I had put the diagonal matrix in front, then I would be multiplying the rows by 2 and by 5.
Oh yeah, okay.
Yeah. So it's because that's the whole purpose. In the textbook, that's kind of just taken for, as you can obviously see, that if. And I'm not convinced that's true. So that's why I've been through that work to see if you post multiply by a diagonal matrix, it's the same as multiplying the columns. So this is a neat, elegant way of, instead of writing 2 matrix equations to express the 2 different eigenvectors, this is a neat, elegant way of expressing all the eigenvectors and their eigenvalues in one go. So that's lambda 1, that's lambda 2, and that's u1, and that's u2. U's are the eigenvectors, lambdas are the eigenvalues, and I've represented that in one go.
So,
Yeah.
I must say, I don't see it like 100%.
Okay, I'm happy to take as much time as we need on this. So, do you want to go back to the? Was it here I lost you up here?
No. I got everything until you started multiplying 2 matrices together. The very last step.
Okay, so you're happy with this?
Yes.
Great. Okay, fantastic. So what this is saying is if I have a matrix times an eigenvector, I get 2 times the eigenvector, and I have a matrix times the eigenvector, I get 5 times the eigenvector. One way of looking at what I'm doing is all I'm after is, can I represent these 2 equations in one go? And matrices are really good ways of representing multiple equations in one go. You can see that with a 3 by 3 matrix, we can represent 3 simultaneous equations. So can I take these 2 equations and write them in one go? Well, what I'm going to do is take matrix. If I do this matrix times minus 1, 1, I get 2 times minus 1, 1. And if I do this matrix times 2, 1, I get 5 times 2, 1. So if I do this matrix times this matrix, which I'm calling the matrix of eigenvectors, I will get the first column will be 2 times minus 1, 1, and the second column will be 5 times 2, 1. Right?
Okay.
Now, can I find a way of taking the matrix minus 1, 2, 1, 1? Can I find something I can do to that matrix that is the same as multiplying the first column by 2 and the second column by 5? And what we found is if we post multiply by this diagonal matrix, that is the same as multiply the first column by 2 and the second column by 5.
I wasn't just sure that you can like just combine 2 vectors and get a matrix and that would be the same transformation.
So that's what I'm saying. Be very careful. The transformation for 2, 1, 3 hasn't changed. Remember, we've done it before where you've got a shape that maybe 5. I could have a 2 by 2 matrix, and I could have 4 points. I could. There's my. So I want to find where the first point goes to, and then I might have another point and I'll do the multiplication again, and I'll find where the second point goes to, and maybe I've got a third point, and I want to find where the third point goes to. I could do it all in one go. We've done this before quite a lot. I will end up with a 2 by 3 matrix. Each column is the image of the corresponding point.
No, it makes sense.
Yeah, okay. But actually, it is important what you say. I am not thinking of this now as a transformation applied to a set of points, particularly. Okay, so this is very abstract. We're not thinking of it in terms of transformations at the moment. We're just thinking of it in terms of matrix multiplication.
Okay.
Okay, any questions so far? Good question, Michael. This, by the way, I think this topic we're doing is the most different from any maths you've done before in the whole course. After eigenvectors, we're going to be back onto more familiar though not easy territory with some integration. So what I can say is if I label my matrix of eigenvectors as U, and I label my diagonal matrix of eigenvalues as D. Yes, sorry, the question? I can say that MU equals UD. That's just our matrix. U is the matrix of eigenvectors. Or them, and D is the matrix, diagonal matrix, for eigenvalues. And what I've shown you is how you can write MU equals UD. Okay.
Sir.
Yes.
Sorry, I was just wondering if you could present it in a pre-multiplying matrix form.
So you mean, could I put the diagonal matrix in front of the...
Yeah, but like you're just, like you're orientating the eigenvector matrix.
As I understand your question, no.
So you're just turning the rows into columns.
Yeah, I mean, if you transposed the matrix, if you switched its rows and columns, but remember, we're not actually, we mustn't obsess over with every matrix, though we have been doing a lot of geometrical work, thinking about matrices as transformations, we mustn't obsess over that, in that matrices can be used for lots of other things that aren't geometric. Are taking sometimes matrices to have columns to represent points is only a sort of tool, it's only an application of using matrix tools. We can't just go, well, I'm going to put that in front there and pretend the rows are columns, because that's not how matrix multiplication works. What we have looked for is if we multiply a matrix by its matrix of eigenvectors, we want something that is a multiple of the eigenvectors. And if you switch that round, it won't work out. They won't be equal.
Yeah, okay, thank you.
Okay, so a sort of typical thing to be asked to do is to diagonalise a matrix. So when you're being asked to diagonalise a matrix, well, actually this textbook thinks of it a slightly different way from how I've thought of it, but they're both equivalent, they're both used. We start with this clear idea, matrix times matrix of eigenvectors equals matrix of eigenvectors times the diagonal matrix, and I'm just going to multiply both sides by U, the inverse of U, and I will get this fundamental equation here. which is, I have written the matrix M as its matrix of eigenvectors multiplied by its matrix of eigenvalues multiplied by the inverse of the matrix of eigenvectors. And it turns out this is really useful. It is really useful to be able to decompose a matrix into this form. Why it's useful, I'm not really going to touch on much today. We'll say a little bit about it, but it's something that I want to show you next week because it's quite fiddly to understand, but I think it's profound. I mean, very broadly speaking, what you're doing is you can turn any matrix transformation into a transformation of the axes followed by a stretch of your shape along those new axes, and then turning the axes back to where they started. But I don't really expect you to understand that, but that's the only answer you're going to get from me until next week when I'll go through it in more detail. At the moment, what you're going to be able to do is this technique of being able to diagonalise a matrix, which means all you have to do is find its matrix of eigenvectors, its diagonal matrix, and the inverse. And in the old textbooks, just in case anyone is looking at them, before this A-level, when NXL did this, they could only do this on a very small number of matrices, a special source of matrices, square symmetric matrices, because it was deemed too difficult and too fiddly to have to find the inverse of any old matrix. But of course, now you're required to have a calculator that can find the inverse for you. So in other words, you can actually do this fairly quickly now. Yeah.
So, isn't U supposed to be matrix of eigenvectors, not eigenvalues?
So U is the matrix of eigen. Have I written it wrongly? Yeah, no, that's right. U is the matrix of eigenvectors.
Yes.
And
if you say
D.
down at point 3, suppose a matrix of eigenvalues.
Oh, thank you. Yes, you're absolutely right. Thank you. Thank you, Michael. We could also have written this in a different way. If we take this equation up here and pre-multiply by U minus 1, we could have got inverse U and U equals D. So we can write the diagonal matrix as U minus 1 and U. And sometimes you'll see questions that ask you to do that. Both of them are said to be diagonalising the matrix. Basically, if you find U, D, and U minus 1, you've diagonalised the matrix. So let's just do this as an example. I have my matrix that we've been working on. We already know its eigenvectors are -1, 1, and 2, 1. And we know the eigenvalues are 2 and 5. So all I need to do now is find the inverse of U. So I'm going to ask someone to find the inverse of U to make sure we can still remember how to do that. Carrie, can you find the inverse of U, please?
I don't think I've got 105.
Oh no! How have we been doing the work before? Okay, so finding the inverse of a 2 by 2 matrix. So these things are fiddly. That's why I've stopped here to remind you to do. I would expect you, all of you, to be able to find the inverse of a 2 by 2 matrix without any further reference to notes. I get that with an inverse of a 3 by 3 matrix, you're probably going to have to refer back to your notes to bed it down. But the 2 by 2 is a nice simple one. Did it last year as well. We've used it a bit this year. Do expect you all to be able to do it. Ella, can you do the inverse of the 2 by 2?
Is it 1, 1, 2 minus 1?
1, 1, 2 minus 1. No, it's not. No.
We do one of the determinants.
Right, first of all, good. You find the determinant. The determinant is -1, -2. So make 1 over notes. So, so the determinant is minus 1 minus 3. The determinant's minus 3, isn't it? And you do 1 over the determinant, so it's minus the third. Yeah, carry on.
And then you change 1 and minus 1 with the positions, right?
You swap the 1 and the minus 1.
And then you put a minus behind the other ones.
And then you. Okay, so actually, it's a kind of annoying example because it looks like I've changed the signs. I've swapped those two, and I've changed the sign of those two. That's how you find the determinant. So we'll just check minus a third, 2/3, 1/3. I do expect you to be able to do that. If you want to check that it works, you'd have to do that multiplication. A third plus 2/3 is 1. Minus 2/3 plus 2/3 is 0. Minus a third plus a third is 0. 2/3 plus a third is 1. So if you're not too good at finding the inverse of 2 by 2 matrices, or not too good at multiplying matrices, you're going to do some practice on it. Okay, so what I'm claiming is that 4, 2, 1, 3 is the same as U times D times the inverse of U. And that is having written n in the diagonalised form. Or similarly, I'm claiming that that diagonal matrix there could be written. Hello, Masha. Of course you can. Yes, thank you. Minus 1, 1, 2, 1. And if we check that, hopefully, hopefully that will give us 2, 0, 0, 5. Don't know if anyone wants to check it for me, but it should do. Okay. All right, we're nearly through with this. I'm going to show you one use of it, and then ask you to do an exercise. Okay. Any questions on that? I mean, what I'm expecting you to do is understand all the steps. What I'm expecting you to do is to get fluent with all the finding the inverse of things. I'm still very happy. In fact, I'd rather it if there were still some of you saying, well, that's all very well, but why on earth are we doing this? Because that is not a question I've really touched on yet, and I will be. Any questions? Has anyone checked? Does this work?
So,
yeah.
I don't really understand, or after that, yeah.
This one, okay, so let me just write U minus 1 n U. So what I did here, Ella, my derivation, I ended up showing that n is equal to U d U minus 1. Are you happy with that?
Yeah.
Yeah, but if I'd have gone here, and if I'd have pre-multiplied both sides by U minus 1, here, to go from here to here, I post-multiplied by the inverse of U. If I pre-multiplied by the inverse of U, I'd end up with D equals U minus 1 and U.
Yeah.
So I was hoping someone would either in their head or get their calculator and check that these three matrices multiplied to 2, 0, 0, 5. But if no one's checked it, then we'll just assume I'm right. Okay. All right, so I'm going to show you one use of it. And this is the use that is most commonly tested in exams up till now. So suppose we can diagonalise a matrix. By the way, it's not always true that you can diagonalise a matrix. To diagonalise a matrix, you have to have both a matrix of eigenvectors and that has to have an inverse. Of course, which might lead to the question, well, what does it mean if you can't diagonalise a matrix? And that's one I'll have to answer when I show you what's actually going on here geometrically next week. But if I can diagonalise it, m squared is u d u minus 1, u d u minus 1. Sam, what does that simplify to?
Is that just u d u minus 1?
Yeah, okay, exactly right. So if I write it, I do a little bit more working than really I would always need, but to be careful, I could use the fact that matrix multiplication is associative. So I get u d I d u minus 1, which is u d u minus 1, which is u d squared u minus 1. In general, a matrix to the power of n can be written as its matrix of eigenvectors times the diagonal matrix of eigenvalues to the power of n, and we'll see why that's useful in a second, multiplied by the inverse. So this is the last example. I'll show you this working. Is any questions on that? Okay. So what have we got? We've got minus 1, 2, 1, 1. Let's admit it back up and see what it is. Minus a third, 2/3, a third. So we know that from what we've just done, I hope you can see if you raise that to the power of 6, you know, you've got that after that, which is I, you end up with now the thing is, to ask you to raise that matrix to the power of 6, if you didn't have a computer to do it for you by hand, it would be really, really difficult. You'd have to do the 6 multiplications. You'd have to find 4, 2, 1, 3, then you'd have to multiply by 4, 2, 1, 3, then you'd have to take that and multiply by hand by 4, 2, 1, 3. Because it's not easy to raise a matrix to power, but the exception is with the diagonal matrix. I want you to work out what 2,0,0,5 to the power of 6 is. It's a special property of diagonal matrices that enables us to do it.
So is it 2 to the 6, 0, 0, 5 to 6?
Yeah. You can verify that by hand, or you can remember that post multiplying by this matrix means you're multiplying the first column by 2 and the second column by 5. So we're multiplying the first column by 2, 5 more times, the second column by 5, 5 more times, so we end up with that. So you can actually raise a diagonal matrix to a power very easy. Whereas it's not easy to raise a matrix to a power, but a diagonal matrix is. And so now we could, to just finish this one off, we could, and it's a bit tedious, this is not going to do it. That times that is minus 2 to the 6, what's 2 to the 6, 4, 16, 64, isn't it? So that's minus 64. And that is 2 times 5 to the 6. And that is 64. And that is 5 to the 6. And then that's equal to 64 over 3 plus 2 times 5 to the 6 over 3. Minus 128 over 3 plus. I'm not going to. And then you can simplify, you can factorise. Simplify. So it's it's straightforward enough to do. Okay, that is where I intend to leave the teaching this morning. Just say the last bit there says another use is related to this geometric investigation, which we're going to look at interpretation, I should say. We're going to look at that later on after we've done an exercise. And that leaves you able to do up to about question 5. Okay, I'm not saying you wouldn't be able to go beyond 5, but I've shown you the stuff that you definitely need up to 5. Beyond that, there's some other stuff I would need to show you tomorrow. So if you have any questions, ask them now. Otherwise, I think I've distributed to you the exercise. Yeah, I've distributed to you the exercise, and as ever at the moment, there are solutions to my work solutions to the exercise are in the content library. So you can crack on with that. As I say, any work you've done, when you finish a topic, and I've set work on it, please make sure at least the front cover with a comment is uploaded to OneNote, so I can just have a quick look. Okay, any questions? No? Okay. Yeah.
Where can we find this exercise?
I've distributed it to you. It's in matrices.
It's 7, right?
Yeah, exercise on eigenvectors and diagonalisation. Is it not showing up for you?
I see. Thank you, sir.
Yeah, and the answers are in the content. The solution. The answers are on the same page, but my work solutions are in the content library. Okay.